Hello everyone, I'm Huiwon Choi from KAIST, and my advisor is Myoungsoo Jung. In this talk, I'll present to you our work, Bridging Natural Resilience and Cost Effectiveness in SSDs for Containerized ML Applications. Before moving on the main talk, let me briefly summarize the work in a single slide. Modern OS-level virtualization technologies such as Docker containers have gained widespread adoption across various domains. Also, many machine learning applications using in Docker container do not require absolute integrity or reliability from their raw inputs, as they inherently poses a certain degree of resilience to data error. By exploiting this natural resilience, we can improve both performance and lifetime of SSDs in container-based systems by relaxing their reliability constraints. To this end, we propose NatureSSD, a novel approach to flash storage allocation that leverages the inherent natural resilience of modern machine learning applications. Now let's move on to the main talk by introducing our background. First, let's go over what Docker containers are. Docker is an operating system level virtualization technology which allows multiple applications to run in isolated environments. A container is an independent runtime environment that runs on Docker, including both the application and all the libraries required for its execution. Typically, multiple containers run simultaneously, each hosting applications with different characteristics and requirements. To address this diversity, Docker allocates hardware resources to each container, according each user's specific needs. One example of such application-specific requirements is latency. For instance, in machine learning workloads, inference tasks are highly latency sensitive, while training tasks are relatively tolerant to delays. Therefore, computation resources can be prioritized for inference containers, while resource limits can be imposed on training containers. By doing so, both services can efficiently meet their respective performance objectives. In this work, we focus on reliability, which is an application-specific requirement often overlooked in existing storage systems. Reliability represents how well data can be preserved and protected from errors inside the storage device. Different application requires different level of reliability. For example, applications that handle critical information, such as password, demand extremely high accuracy and therefore must ensure strong data integrity. In contrast, applications such as machine learning can tolerate small data errors and still operate normally. Therefore, providing uniformly high reliability for all applications is unnecessary and inefficient. However, current system forces SSDs to guarantee the same high reliability for all containers, regardless of the type of the data they store. As a result, SSDs provide excessive reliabilities, which lead to shorter lifespan and increased latency due to the unnecessary error correction operations. Next, I'll explain some backgrounds to help understand why the reliability levels that an SSD provides is closely tied to its lifetime and latency. As flash blocks go through repeated program and erase cycle, or PE cycles, the likelihood of data errors gradually increase and the device becomes less reliable. This happens because each PE operation applies a high voltage to the memory cells, which slowly alters their electrical characteristics over time. To mitigate this issue, SSDs employ error correction code, or ECC. Before correction, the error rate is called RBER, raw bit error rate, and after correction, it is called UBER, uncorrectable bit error rate. Modern SSDs primarily use low-density parity check or LDPC codes for error correction, which consist of 7 decoding levels. Higher LDPC levels perform more read-retry operation, improving correction capability but also increasing read latency. When the UBER exceeds 10 to the minus 15, the blocks are no longer considered usable. As the cells get older, they require higher levels of LDPC decoding to keep the UBER low. Therefore, providing high reliability leads to two major inefficiencies. First, blocks with many PE cycles can no longer provide sufficient reliability, and therefore they cannot be used. This reduces the usable lifetime of SSD. Second, when older cells are still used, they require higher LDPC decoding levels to maintain reliability, leading to the longer lead latency. Next, I'll explain the motivation of NatureSSD. We found that the inefficiency we discussed earlier can be addressed by supporting different levels of SSD reliability for different applications. To illustrate this concept, please consider the following figure. On the x-axis, we have the raw bit error rate, or RBER, which increases as flash blocks gets older. On the left y-axis, we have the uncorrectable bit error rate, or UBER. A lower UBER indicates higher reliability. The solid curves show how each LDPC level can enhance the given RVER to its corresponding UBER. While higher LDPC level can tolerate higher RVER, they also introduce longer read latency, since more read and retry operations are required. Now, typically, SSDs must meet the fixed reliability standards of 10 to the minus 15, which correspond to these green lines shown in the figure. However, if we know that certain applications have natural resilience to bit errors, we can relax the reliability standards for those workloads, which corresponds to this blue line shown in the figure. When we compare these two lines, we can see that for the same aged block, relaxing the reliability requirements allows the SSD to operate with a lower LDPC level, which means lower latency than the baseline. Also, for the same LDPC level, it also allows the SSD to operate with the older block than the baseline. Building on this idea, we propose NatureSSD, which allocates SSD resources differently according to each container's reliability requirements, thereby improving both SSD lifetime and performance compared to the baseline. To realize NatureSSD, several enhancements must be made to the existing systems. First, the system should allow each container to send its reliability requirement to the SSD. Second, the SSD should be designed to allocate blocks according to this reliability requirement. To solve this problem, we introduced two key components, the QoS-aware OS level virtualization and QoS-aware block allocation. Now I'll explain about QoS-aware OS level virtualization, which delivers reliability requirement information to the SSD. The overall data flows can be divided into the two main parts. First, the paths where user-defined information is passed down to the kernel space. And second, the paths where the kernel-level information is transmitted down to the storage stack. For the first part, we extend the cgroup v2 block I/O controller to include two new parameters, I/O resilience, which represents the application's tolerance to bit errors, and I/O read latency level, which indicates the required read latency level. As shown in figure, the QoS information flows through the Docker stack. When a user specifies QoS value in a JSON file, the Docker client sends them to the Docker daemon via HTTP. The Docker daemon then passes the data to container daemon using gRPC over Unix sockets. And finally, the Docker runtime writes these values to the kernel control files using the standard write system call. Through this process, each container's new QoS requirements informations are properly registered in the kernel. For the second part, we utilize the RSVD2 field of the NVMe read-write command structure, which was previously unused. To transmit this QoS information to the SSD, this field now carries the reliability and the latency parameter defined by each container. As shown in figure, the QoS information flows through these data structures. I/O requests are processed through the block I/O request and NVMe read-write command structures in the Linux storage stacks. Each block I/O structure contains a pointer to the BLKCG, the container cgroup, and each request structure contains a pointer to its corresponding BIOS. By following this link, the kernel can access each container's QoS data when constructing the NVMe commands. Now that we understand how the reliability information is delivered to the SSD, let's take a look at how the SSD controller allocates free block using this information. When an NVMe commands arrive, the SSD controller takes the command's read latency level and error resilience value as the inputs to the mapping table, which outputs the corresponding group ID. Once the group ID is determined, the controller refers to the free block pool structure to locate a free block that belongs to the same group. Among the free blocks in the group, the controller selects the blocks with the highest P cycle count. The approach helps to preserve newer blocks, thereby extending the SSD's lifetime. Each block's free block are organized as the red-black tree based on their P cycles, so the block with the highest P count always resides at the bottom right of the tree, making it easy to find and locate efficiently. Lastly, let me introduce the evaluation results of NatureSSD. For the evaluation, we modeled SSD lifetime based on the prior research. As the workload, we used the MLPerf benchmarks, which covers diverse machine learning domains. Our testbed is configured as follows, and our proposed QoS-aware NVMe interface and block allocation mechanism were implemented using NVMe BERT, which manage all data read and write operations. First, we evaluate SSD endurance while maintaining various levels of end-to-end performance. Results show that the NatureSSD extends the SSD lifetime by an average of 42.7% compared to the baseline. Next, we also evaluate application performance across SSDs at different aging levels. NatureSSD consistently achieves about 17.6% higher performance than the baseline. This improvement comes from the NatureSSD's ability to leverage application-level resilience to relax UBER requirements. In the multi-tenant scenario evaluation, multiple applications with different levels of resilience run concurrently. The figure shows the P-cycle distribution of the SSD blocks. In the baseline, block wear is almost uniform across all applications since their QoS differences are ignored. In contrast, NatureSSD generates distinct P-cycle distribution for each application, reflecting differentiated block allocation based on QoS requirements. By assigning warm blocks to error-tolerant application and reserving younger blocks for critical ones, NatureSSD improves block utilization and effectively extends SSD's life. In conclusion, we introduced NatureSSD, a novel approach to flash storage allocation that leverages the inherent resilience of machine learning applications in containerized environment. Thank you for listening.